In a 208 volts Y system, the line-to-line voltage is approximately 360 volts. This is determined by multiplying 208 volts by the square root of 3. In a 240 volts delta system, the line-to-line voltage is 240 volts. Since the line-to-line voltage in the delta system is lower than in the Y system, the current flowing through the meter will be lower as well. This results in an under-registration of the actual energy consumption. The error in kilowatt-hour consumption can be calculated using the following formula. Error in percent equals the quantity of actual kilowatt-hour minus apparent kilowatt-hour divided by actual kilowatt-hour, the whole quantity multiplied by 100. The apparent kilowatt-hour consumption is the reading displayed by the 240 volts delta meter. The actual kilowatt-hour consumption is the energy that would have been consumed in the Y system. The apparent kilowatt-hour consumption can be calculated using the following formula. Apparent kilowatt-hour equals apparent power times time, where apparent power equals the quantity of voltage times current times the square root of 3. The actual kilowatt-hour consumption can be calculated using the following formula. Actual kilowatt-hour equals actual power times time, where actual power equals the quantity of voltage times current times power factor. The power factor in a balanced three-phase system is power factor equals cosine of phase angle, where phase angle equals 120 degrees for a Y system. Substituting the expressions for apparent power, actual power, and power factor into the error equation, we get error in percent equals the quantity of voltage Y times current Y times time Y times cosine of 120 degrees minus the quantity of voltage delta times current delta times time delta times the square root of 3 divided by the quantity of voltage Y times current Y times time Y times cosine of 120 degrees, the whole quantity multiplied by 100. Simplifying, we get error in percent equals the quantity of voltage Y squared divided by voltage delta squared minus 1, the whole quantity multiplied by 100. Substituting the given values, error in percent equals the quantity of 208 squared divided by 240 squared minus 1, the whole quantity multiplied by 100, which equals approximately negative 18.75%. Therefore, the 240 volts delta meter under-registers the actual energy consumption by approximately 18.75%. In essence, the error arises because the meter is calibrated for a higher voltage than what it is actually measuring. The kilowatt-hour meter is designed to accurately measure energy consumption at its rated voltage, in this case 240 volts. When it's used on a 208 volt system, it doesn't account for the difference in voltage, leading to an inaccurate reading. The meter is essentially underreporting the amount of energy being used. This underreporting occurs because the meter is sensing a lower voltage than it is designed for. The lower voltage results in a lower apparent power calculation, which subsequently leads to a low kilowatt-hour reading. It's important to note that this error is significant, approximately 18.75%, which can lead to substantial discrepancies in billing and energy management. To correct for this error, it's necessary to use a meter that is properly rated for the 208 volts Y system. Using the correct meter ensures accurate measurement of energy consumption and avoids the underreporting issue. The mathematical equation provides a way to quantify this error, allowing for a better understanding of the discrepancy between the apparent and actual energy usage. The equation highlights the relationship between the voltages of the two systems, Y and delta, and their impact on the overall error percentage. The simplification of the equation makes it easier to calculate the error, providing a practical tool for engineers and technicians. The substitution of the given values 208 volts and 240 volts into the equation demonstrates the specific error that occurs in this scenario. This calculation reinforces the importance of using the correct meter for the specific voltage system to ensure accurate energy measurement and billing. Furthermore, the equation emphasizes the significance of the power factor in energy calculations. The power factor accounts for the phase difference between voltage and current, which affects the real power consumed. In a balanced three-phase system, the power factor is determined by the cosine of the phase angle, which is 120 degrees for a Y system. This power factor is crucial for accurately calculating the actual kilowatt-hour consumption. The apparent power, on the other hand, is calculated without considering the power factor, leading to a discrepancy between the apparent and actual power. This discrepancy is what causes the error in kilowatt-hour consumption when using the wrong meter. In summary, the error in kilowatt-hour consumption when using a 240 volts delta meter on a 208 volt Y service is due to the voltage mismatch between the meter's calibration and the actual system voltage. This mismatch results in an underreporting of energy consumption, which can be quantified using the provided mathematical equation. The equation takes into account the voltage difference, power factor, and other relevant parameters to accurately calculate the error percentage. Using the correct meter for the specific voltage system is essential for accurate energy measurement and billing. This explanation provides a comprehensive understanding of the error and its underlying causes, enabling engineers and technicians to make informed decisions about meter selection and energy management.